Okay, so the problem says that we have two tanks. This is tank 1 and tank 2. We have a flow coming in. This is Q1. And then from tank 1 to tank 2, we have Q1, 2. And then out, we have Q2. Now, we'll assume that we use water for this one. Although, one assumption for this is that the density is constant. So whatever it is, it's the same liquid, or the density is constant. So we will have a height 1, height of the liquid in tank 1, and then a height of the liquid in tank 2. Okay. So since density is constant, we can use a volumetric balance. We know that the change in volume over time will equal the difference of the two flow rates going in and going out. So we can use the concept for both tanks. We'll have two different systems, and that's how we're going to find it. So for one tank, we'll have the change in volume over change in time is equal to the flow rate going into tank 1 minus the flow rate going out of tank 1. Okay, well, we also know that volume is equal to the area times the height. So plugging that back in, we get change in area of 1 times the height of 1 over change in time equals Q1 minus Q12. Okay, well, the area will not change for the tanks, only the height will. So we can divide both sides by that. So we get the change in height of 1 over change in time equals Q1 minus Q12 all over A1. Okay, we can use the same principles for the other tank. So this is for tank 1, and then for tank 2, we have the change in height in 2 over change in time equals Q12 minus 2 over area of the second tank. Okay, now from our the problem we were given, we were told that the flow rate of 1, 2 is equal to alpha times the square root of h1 minus h2, and that the flow rate going out of the second one is equal to alpha times the square root of h2. Now we're given alpha. All the variables we're given that the area of tank 1 is equal to 1 meter squared. Area of tank 2 is equal to 1.5 meters squared. Alpha of 1, 2 is equal to 0.5. Alpha of 2 is equal to 0.25. The height at 1 is equal to 2 meters. The height at 2 is equal to 1.5 meters. And then we want to find, we want to solve the resulting initial value problem using Python, and we also want to derive the governing equation and the initial height of tank 1 and 2. So we want to do this from time interval 0 to 50 seconds and 50 seconds to 100 seconds. We also know that Q1 is equal to 1 meter cubed per second, and that this is for the first time. From 0 to 50, the flow rate in to the first tank is 1 meter cubed per second, and then the flow rate changes from 50 to 100. It goes from 1 meter cubed per second to 1.5 meter cubed per second. Okay, so the first thing we want to do is we want to import everything. So we're going to import the integrate function. So, from sippy.integrate import solve underscore IVP. We're going to import numpy as np. We want to interpolate, so from scipy.interpolate import inter 1D. We want to be able to do subplots and plots, so from plotly dot subplots import make underscore subplots. And then lastly, we want to import plotly.io as, okay, we'll run that. And I did not spell that right. Integrate, there we go. Okay, good. Okay. From here, we want to make our function. So we're going to define the function as the change in height over time. And we'll make t and z are two variables. Okay, so then we want to do height 1 is equal to the first value of the array. I'll make the array here in a second. And then height 2 will be the second value in the array. And then we need to do the flow rate equations. So Q12 is equal to alpha of 1, 2 times NP dot the square root of height 1 minus height 2. Perfect. Okay. And then we want to do the flow Q2 is equal to alpha 2 times NP dot the square root of height 2. And then our change in height 1 is equal to the flow rate going in at a function of time, minus the flow rate going out, all divided by a 1. Let me get rid of that. And then the change in height for the second tank is equal to Q12 minus Q2 divided by the area of 2. And then we want to return, change in height for 1 and the change in height for the second one. Good. Okay. All right. Now we're setting all our variables. So we're going to do A12 is equal to 0.5. That's what was given to us. We'll do A alpha 2 is equal to 0.25. A1 is equal to 1. A2 is equal to 1.5. And then we'll set our Z. The first one is 2, and the second one is 1.5. Now our Q underscore V, which is our would be, we'll set that as an array of 1, then 1.5, 1.5, and then we'll set another array. Our time interval will be 0 to 50, and then to 100. All right. Now our Qn, this is going to be the interpolated one. Spelled that wrong. Interp 1D, and then we'll do Q underscore T, Q underscore, nope, already did that, B, and then the kind we will do previous. Oops, spelled that wrong. Previous. Okay. Now we want to res equals solve underscore IVP. Then we want to change underscore age, call the function, and then we'll go from, sorry about the noise. We will go from 0 to 100. Then we'll use Z. And the method will be and we'll do dense underscore output equal to true. Then what's our t value is equal to np linspace from 0 to 100. Zero to 100 by 100. And then we will equals res dot sol of t. Then for the figure equals make underscore subplots. And then we'll have row equals 1, and then columns also equal 1. Now we're going to add the figure, so fig dot add underscore scatter. This will be x equal to t, and then y equal to sol of 0. Then the name will be equal to h1. Okay, so we want the second one. We'll copy and paste this. This will be the second. this will be the height too. And then lastly, we want to get the graph all together. So fig.update underscore layout. The width equal to 500, the height equal to 400. We'll do x-axis underscore title equal to time. And then we want the y-axis underscore title equal to height. And then the whole title of the whole chart will be called 2 tanks. Oh, 2 tanks. And then we'll have the title underscore x equal to 0.5. And then we want to show the figure. All right. So this is the graph.